In this video, we're going to look at sound intensity and the decibel scale. So sound waves carry energy that can be used to do work. And the amount of energy that's transported per second is called the power of the wave. Just like before when we talked about power being a rate of energy. Well, when we talk about the power of a sound wave, we're talking about the same thing. It's a rate of energy that is transported per second. And the sound intensity, when we talk about the intensity of sound or the sound intensity, we define that as the power that passes perpendicular through a surface divided by the area of that surface. And we will represent the intensity with an I and say that that is the power divided by the area. Notice as the area gets bigger, the intensity decreases. And so looking at this diagram of two people standing next to a source of sound here, some speaker, the area of region 1 is much smaller than the area of region 2, and so the intensity is going to be lower at 2 than it is at 1, even though the power output may be the same. So if we put some numbers here and we look at the fact that we have a sound power output of 12 times 10 to the negative 5th watts, and it passes through these two regions, 1 and 2, where 1 has 4 square meters of area and 2 has 12 square meters of area, we want to determine the sound intensity at each surface. So we can use our formula that the intensity is equal to the power divided by the area, and we can look at surface 1 and take the power of 12 times 10 to the negative 5th watts divided by 4 square meters, and we get an intensity of 3 times 10 to the negative 5th watts per square meter. Now this is an important unit here. This is a unit that is a little new to us, and we're going to use this in this video and further in the course. It's watt per square meter, so that's power per area. And we can do the same thing for region 2 using the same numbers, except we change out the area here and we find that we have a lower intensity of 1 times 10 to the 5th. So it's 3 times as much area in region 2 as region 1, and we notice we have 1/3 of the sound intensity. For 1,000 hertz tone, so that's a tone that is vibrating 1,000 times every second, the smallest sound intensity that the human ear can detect is about 1 times 10 to the negative 12th watts per square meter. So that's pretty small. That's a tiny little bit of energy every second that is coming through every square meter surface. And this intensity is called the threshold of hearing. Anything below this, any power less than this, we can't detect it. Our eardrums won't respond to it, and it won't create enough of a disturbance inside of our ear to create the electrical impulse in our auditory nerve. However, on the other hand, continuous exposure of intensities greater than 1 watt per square meter, so just 1 watt per square meter, that can be extremely painful, and in fact that can start to rupture your eardrum and make you bleed from the ears. And so those tiny little bones that are in your ears that vibrate, that help vibrate the fluid that translates into the auditory nerve, those bones can break. And so any intensity bigger than that, we're going to have some issues in our ear. And if the source emits sound uniformly in all directions, then the intensity depends on the distance from the source in a pretty simple way. The key is it has to emit uniformly. So thinking of a speaker, that's not going to be uniformly in all directions. A tuning fork is going to be pretty close. It's going to go in all 3 dimensions. And so the way that it emits, it's going to propagate out in a spherical wave form, where the source is at the center of this spherical shell. And so that means that our area is going to be the surface area of a sphere, which is 4 pi r squared. So what this does, this allows us to realize that we have this inverse square relationship. As we get farther from the source, if we double our distance, we are going to cut our intensity by 1/4 because we are squaring the distance in our area formula. So that shows us a little bit that our intensity is going to decrease by the inverse square law. Let's look at a conceptual example here. And suppose we have a person singing in the shower and they produce a sound of power P. And sound is going to reflect off of the surrounding shower stall, the ceiling, the walls, and all that. And so as the sound is emitted, it's going to hit the ceiling and reflect back down, and it's going to hit the floor and reflect up. And then some sound is just going to propagate straight out. And so at a distance r from the person, how does the equation for the intensity of sound emitted uniformly in all directions, is it an underestimate, overestimate, or is this the correct sound intensity? So this is asking, is this equation correct in this case, where the intensity is equal to P over 4 pi r squared? Now keep in mind, this equation is for something that propagates spherically. And if we didn't have the shower stall, if we didn't have the ceiling, the floor, or the walls, then yes, this would propagate fairly spherically in that it would go in all directions, and we would abide by this inverse square law, and I would be equal to P over 4 pi r squared. But what's happening here? Well, part of the energy that's being sent upward is hitting the ceiling and reflecting back down. And so the energy that we would expect to be off in this direction over here is actually located down here at our point of concern. And the same thing happens as the energy goes down, it's reflecting back up. So really this intensity equation is an underestimate of what's truly happening at that point in the shower. And so this is typically why if you're at home singing in the shower, you tend to sound a little better because your voice is getting amplified and you're getting these overlay of harmonics. And so that's why in recording studios, they're going to put you in a little box to help that sound bounce off of it and reverberate back. And in fact, some of the earliest recording studios back before they had nice sound technology, they would have you project your voice into this tile box that was kind of designed like a shower stall, just a lot smaller, and then they put the microphone in that box, and so you sang into the box and they would bounce around and it would intensify the sound. So we need a scale to talk about and to quantify this measure of intensity. And so this is where decibels come in. And I'm sure that you've heard the term decibels before and you know that it deals with sound. However, the decibel scale is not very intuitive in that it's not a linear scale. When you think of temperature, when, as the temperature rises, the internal energy of the room is rising and it feels warmer and all that. Well, yeah, that's true with the decibel scale, but it doesn't move in a linear fashion. It's a logarithmic fashion. And so that may be a little counterintuitive. So before we get into the mathematics of it, let's talk about the idea behind it, in that a decibel, and we use dB, lowercase d, capital B, to signify a decibel. It's a measurement unit used in comparing two sound intensities. And this is important. We're using it to compare sound intensities. This is the intensity level, but we're using it to describe intensities. And so we have to make sure that we're clear on the semantics here because they mean two distinctly different things. Because of the way in which the human ear works and how it responds to intensity, it's appropriate to use a logarithmic scale called an intensity level. So when we're talking about intensity level, that is not the same thing as the sound intensity. Sound intensity is I, that's the power per unit area. Intensity level is measured in decibels. And we find that we use the capital beta to denote the decibel, and that's equal to 10 decibels times the logarithm, and this is log base 10, the logarithm of the intensity divided by this reference intensity that we want to use. And because we typically want to deal with human ears, we use the threshold of hearing as the reference intensity, and that's the 1 times 10 to the negative 12th watts per square meter. Note that the log of 1 is equal to 0. So when the intensity of sound is equal to the threshold of hearing, the intensity level is 0. So right here, this shows that the intensity level and intensity of sound are two different things. We have a sound intensity of 1 times 10 to the negative 12th watts per square meter. That's the sound intensity, or the intensity of sound. And the intensity level measured in decibels is 0. Because if we put in 1.1 times 10 to the 12th in here and then divide by 1.1 times 10 to the 12th, or negative 12th, excuse me, that gives us a 1, and log of 1 we know is 0. To give you an idea of some reference points here of decibel levels and intensity levels and sound intensity, the threshold of hearing is 1 times 10 to the negative 12th watts per square meter. That's the intensity, and the intensity level, 0 decibels. Well, a whisper, just someone whispering in your ear, that's about 1 times 10 to the negative 10th, so that's 100 times bigger than the threshold of hearing, and so that is 20 decibels. Okay, notice 100 times bigger, 20 decibels. 10 times bigger, 10 decibels. So you would think 1,000 times bigger would give you 30 decibels. And so notice that's why we have this logarithmic scale, and we're multiplying by the factor of 10 decibels. And so normal conversation, just someone talking to you at 1 meter is going to be 3.2 times 10 to the negative 6 watts per square meter, about 65 decibels. Now, I will let you know, my typical conversation voice is closer to 80 or sometimes even 85, depending on how close you are to me when I talk. I'm a little louder than the average person, so that can range, but a typical conversation is probably around 65. Now, you can get up to a rock concert. It's going to be about 1 watt per square meter, and that's 120 decibels. And remember, that starts to cause some damage in your ear. And if we get to 130 decibels, or 130 decibels, excuse me, that's where we reach the threshold of pain, and we actually start causing severe pain in the eardrum and causing damage that cannot be reversed. Let's take a look at an example of comparing sound intensities. So we have an audio system 1 that produces a sound intensity level of 90 decibels. So this is intensity level. This is talking on the decibel scale. And we have system 2 that produces an intensity level of 93 decibels. And so we want to determine the ratio of the intensities. You might think, oh, that's just 3 more decibels. That's not a whole lot more. You know, it's not creating that much more sound or that much more power output. But really, remember, this is intensity level, and it's a little deceiving of a scale because it's a logarithmic scale. And so when looking at this, and this kind of tells the story a little bit in that we have a 20-watt system and a 200-watt system, but we'll get to that in a second. So if we use the decibel equation here, we know that the ratio of intensities is going to come into play here when we want to find the scale. So let's find the intensity of each of these two systems using this equation. So using this equation, we're going to look at system 1 and system 2, and we're going to find what is the intensity of 1, what is the intensity of 2. Well, we can subtract these two and subtract the logarithms, and this uses a few logarithm rules. If you're unfamiliar with that, you might have to revisit some of your old algebra techniques here. So when we subtract the two betas, we get a difference of 2 logs. When a difference of 2 logs, we actually get a ratio inside the logs. And notice the threshold of hearing cancels out, and we just get the log of I2 over I1. And so we can solve this to say that, well, we have a difference of 3 decibels. That corresponds to 10 times the log of the ratio of those two. And solving this, we have to exponentiate. So once again, this is going to be some algebra that you may have not used in a while. We have to exponentiate and see that if 0.3 is equal to the log of the ratio of intensities, then the ratio of intensities is equal to 10 to the 0.3 power, which is 2. So that shows you that we have twice the intensity in system 2 than we do in system 1. And you might think, now wait a minute, that was only 3 decibels. But that 3 decibels actually corresponds with twice the energy. Now keep in mind, this is not always the case that 3 decibels corresponds with twice as much. It's 90 to 93 decibels. That's the difference here. Going from 90 to 93 decibels, we're actually increasing the intensity by a factor of 2. So we will continue to work with these equations and this scale more in class.